Let me start about the short introduction to GPU programming. So what is GPU? We all know that we have CPU in the computer, which is the central processing unit. In the computer, for GPU, it is called graphic processing unit, which is a specialized electronic circuit. Originally, a GPU was developed for computer graphics and image processing. Now, at the current stage, GPUs have evolved to general proposed accelerators for massive parallel computing. It's super powerful for this parallel computing. Here I show some GPU card. Here the GPU card from NVIDIA RTX 4090. If you are a game player, you will get familiar with this one. It's super powerful, this computer game. You can experience ultra high performance gaming, incredible details of the virtual world. The right one is NVIDIA H200 GPU card, and this also it has advanced performance capabilities, and is the most complete and powerful platform for AI-based research. In addition to NVIDIA, AMD and Intel, they have their own GPU cards. Here one is a AMD MI300 series, and here is one Intel Arc series. For these GPUs, they offer exceptional computer performance, large memory density with high bandwidth, and also support to specialize the data format. Yeah, from the outside, it's difficult to ask what's the difference between this GPU card and also between CPU and GPU. But if we come to the internal structure, we can figure out there's a significant difference between CPU and GPU. Generally, CPU and GPU are discrete processing components. If you have a GPU card in your computer, you know that you can see that the GPU and the CPU are connected by a PCI Express bus for the data transfer between CPU and the GPU. Both CPU and GPU have a similar internal component. For example, arithmetic logic unit, control unit, cache unit, and the memory part. But they have a significant difference on this part with their functionalities. GPU has quite complex core structures and dedicated a large area to the control unit and the cache unit. Well, for GPU, it's quite simple. You can see that GPU, there are 100,000 of arithmetic logic unit ALUs right here to achieve a high compute density in the GPU card. Yeah, because of the difference in the internal structures in CPU and GPU, they have different functionalities. Yeah, I mean that CPU is quite powerful for the control unit right here and also cache unit. They can rapidly switching between different instructions, while GPU core is somewhat more powerful but less simple. And you can see that GPU are quite excel in parallel processing simple and repeating tasks through these hundreds of thousands of arithmetic logic units. I should say that GPU, currently, it is not a standalone platform, but it is a coprocessor to the CPU, which means that CPU always work together with GPU always works with the CPU in the computer. In most cases, CPU refers to the host and the GPU refers to the device. And the GPU mainly for the data caching and also the flow control, and the GPU for this parallel data processing. And because of this superpower in the computing, GPU are the workhorse for many HPC systems. HPC means high performance computing systems. Here is the list of top 10 HPC systems in the world. This list was released last June, and a new one will be released in November, I think in the beginning or the middle of November next month. So we'll see there's some update about the list. From this list, you can see that for these 10 HPC systems, 9 of them are equipped with GPU card, except the number 4, Fugaku. This is the machine in Japan. It's quite a special one, equipped with ARM CPUs. But for others, you can see Frontiers equipped with AMD GPU card. For number 2, Aurora is equipped with Intel GPU card. And the third one is NVIDIA GPU H100. For these top 10 machines, you can see that in Europe, we have 4, which are number 5 for the Lumi, which is located in Finland. We use this one a lot for the training. And number 6, Artis in Switzerland. We never come to this one, but if we have the opportunity, we'd like to try to use this one. Number 7, Leonardo Booster. Leonardo in Italy, we use a lot for this one for our training event. And number 8, Nostrum 5. This machine is not available, not ready to use, but we would like to see its usage in the next year, probably. Yeah, because of these superpowers provided by the GPU card, researchers can use these HPC machines to solve problems involving larger amounts of data analysis or data parallelization. For example, the graphic rendering, computer vision, and also the computer games. And if you are working on the natural science, you can use these HPC machines for molecular dynamics, Monte Carlo simulations, and also the computer fluid dynamics. That is my colleague Ashwin's territory. For AI-based research, you can also use them to handle large-scale metrics, window operator, frontier transformation, and also the convolution neural networks. Yeah, even this can also be used in cloud computing and also the quantum computing. We can see the era of HPC plus QC is coming. QC means the quantum computing. Now here we just talk about the GPU hardware. And actually, not only the GPU hardware, GPUs come together with a sort of software or API, a software stack or APIs. APIs, the application programming interface. Here, as I mentioned before, there are 3 main GPU vendors, means NVIDIA, AMD, and Intel. These vendors not only design GPU, but also reproduce GPU with their own specific APIs. For example, NVIDIA has CUDA, and AMD has ROC, and Intel has one API. These APIs not only provide a standard way for the software to interact with GPU hardware and so as to achieve a better performance and portability for the GPU programming. Typically, these APIs enable the programmers or developers to access to the GPU functionality at the 3 levels. At the low level, it will handle the memory management, the data transfer between CPU and the GPU, and also the scheduling and execution of parallel processing on the GPU. And for the high level part, at the management of modules and libraries that can be optimized for this specific HPC workload and also AI-related applications. These APIs can also provide some debugging profiling tools for optimized code. As mentioned, these APIs right here, it is platform dependent, which means that CUDA only works for the NVIDIA GPU and the ROC for AMD GPU and one API for Intel GPU. Besides these platform dependent APIs, there are also some other ones called cross-platform APIs for example, direct compute, OpenCL, SQL, and this webinar, I'm not going to talk too much about these APIs. You can Google to see the specific functionalities for these different APIs. If you want to learn more, you can come to our workshop, GPU programming, why, when, and how, which will be available next month from 12 to 14. You can register for our workshop to get more information about the GPU programming. Yes, now we know what is a GPU and the difference between CPU and the GPU. How does the GPU work for this computing? There are different ways, I can say, to use the GPU for the computation or for the computing. GPU computing, or we can also say the GPU programming, it does not mean to replace CPU with GPU. In most cases, GPU and CPU work together, in which CPUs take the control-intensive tasks and the GPUs are responsible for the data parallelization, computing tasks. So for the GPU programming, there are several programming models. There can be directive-based models. It can be non-portable or portable kernel-based models, and also there are some high-level programming languages. Oh, right. Down. For directive-based programming models, this model means that you have the source code, serial source code, and you can provide something to the serial source code so that to tell the compiler that which part or which loop should be run on the GPU part, GPU part. To represent the directive-based programming models are OpenCC and OpenMP. I here provide two examples. The left is written in C, and it is for the OpenCC. See, you can see if you provide some directive right here, program ACC kernels, this will tell the compiler, okay, this for loop will be executed on GPU. This red part is also language written in Fortran. You can use OpenMP. You can provide the program like this, OpenMP target, and the compiler all knows that, okay, I will ask the GPU to run this do loop on the GPU part. You can see that this programming model is relatively straightforward. Just provide some keywords right here, directive right here, and the compiler can manage the left things. So which means that it allows the minimum programming effort by adding some parallelism to existing code without need to write a specific code for the acceleration. But such a way means that it might be not so good with not high efficiency. So if you want to really achieve a high efficiency of your source code, you can use non-portable based models. In this model, it is known as the native programming models, which means that we use CUDA for the programming using NVIDIA GPU, and we use HEAP for the AMD GPU. And these are the two representative models, CUDA and HEAP. In these models, here is the code example about the programming using CuDA-C. The basic procedure is that we initialize the data on the CPU part and transfer data from CPU to GPU, and then do the data processing or calculation on the GPU part, and then transfer data from GPU to CPU, and then finalize this programming. It's somewhat simple, right? But how to handle the data transfer from between CPU and GPU, and this is take lots of time for you to handle it. Next is the portable kernel-based method. You can call it cross-platform portability ecosystems. This system typically provides a high-level abstraction, which provide convenient and portable programming models for this GPU programming. Yes, there are some models like Alpaca, Cocos, OpenCL, and SQL. I'm not going to talk about details about these programming models. And if you really want to know, you can come to this right link to see their specific functionalities, or you can come to our website on our lesson materials for self-learning about the GPU programming workshop lesson materials. Yeah, but I see that there are some cons and pros of this cross-platform portability system, but we are lucky enough because we have some high-level programming languages can be used for the GPU programming. For example, Julia and also Python. In this part, the main theme of this webinar is Python, and next webinar we'll talk about Julia, GPU programming using Julia. Yeah, now my part is done. I hand over the word to my colleague Ashwin.
Thank you, Yongle.
Yeah.
I am hoping that a lot of you already familiar with Python, but just in case if somebody doesn't use Python as their not daily driver programming languages. I prepared a small little introduction on how a Python syntax would look like. So as a prerequisite for this webinar, so that you will follow whatever I'm speaking, you would have to know like how integers are represented in Python. Like, as you know, Python is types are inferred, but types are, strongly typed. So types are actually respected. So if you write without a decimal point, it's an integer. With the decimal point, becomes a float. And you can use single quotes or double quotes to write strings, and triple quotes to write multi-line strings. There are, of course, data structures to form collections of these individual scalars. So some of these common data structures are lists. Lists are mutable, but they are ordered. So here is an example of a list. Tuples expressed by these parentheses are immutable. So you cannot modify a tuple once it's created. There are, of course, dictionaries, which represents key value pairs, and sets, which are unique unordered collections. Sorry, it's not a sequence. If else expressions are used for conditional execution. So they evaluate an expression, and then one of these statements would be executed. This is very simple. It almost looks like pseudocode in Python. And of course, there are loops, a for loop and while loop, where you have to break to come out of it. Functions are also very often used to structure reusable parts of reusable codes. There are some built-in functions, and of course, there are also user-defined functions. Len and types are examples of built-in functions. Print is also another built-in function. So these are functions which come without importing any module from Python. And maybe a less common feature, but it's very useful, is called decorator. A decorator is a special syntax added on top of a function, which would modify the behavior of it. You hear LRU cache is one such decorator, which is very often used to speed up the performance of a repeated function call. And you can look at these library tools to create your own decorators. But we will be using these decorators quite often in this webinar. There are other very cool Python features which we won't be needing, but they are good to know. So if you're interested, take a look at type annotations, classes, and so on. This webinar is demonstrated using Jupyter. We don't use the whole fancy features, every feature of Jupyter, but it's good to know some of them because we are showing that. One of that is this special variable called underscore. So if you execute an expression in Jupyter and then you get a result and you want to reuse that result, you can use this underscore. So here, by doing so, I get that back from the previous execution. There are some special commands which look like shell commands. One such is called time. These commands are called magic commands in Jupyter. So what time does, it evaluates and records the time taken for executing one Python expression. Very useful for checking the performance. But of course, one execution is not a good statistic. So we need to do repeated evaluation for proper benchmarking. So in order to do that, we use time it instead. Here by this, we create a list, and then we run a small benchmark using time it, which runs it for 1,000,000 times and then gives you the mean and the standard deviation. So you get a more reliable number. Of course, you can do a micro benchmark for a set of lines or a block of Python code. And for that, you use this double percentage time it. And here we see that happening, and then we get the result to the end. We'll be using these two and this underscore in this webinar. Yeah. So before we jump right into the different libraries which lets you program GPU, it might be also useful to look at how you do programming with numbers and Python using these three famous scientific libraries, Numpy, Pandas, and Matplotlib. Here I will be using this function. We don't need to look into that. But NumPy, more importantly, NumPy is used to represent arrays. Arrays are typically uh, contiguous data of particularly used to store numbers such as integers and floats. It can be of any dimension, like ranging from 0 dimensions to n dimensions. So if we are just stuck with standard Python, vanilla Python, we would be using something like a list to build a list of numbers. And then let's say we need to calculate the squares of this list and store it into this other list called B. Then we would be doing a for loop. But we all know that for loops are terribly slow. So if we keep that, record that timing, it's always better to go for such applications to use NumPy instead, where you have a more terse syntax, a more shorter syntax, and it's often vectorized. So if we just compare those two timings, we see that there is orders of magnitude in difference for this very trivial example. So yes, and one quick note, NumPy is often imported as NP, and this is a very common convention in Python world. NumPy arrays can be created out of lists like this by calling NumPy array. You can interrogate by using these properties called shape and size to know what the dimension is, the number of elements the array contains. And NumPy is often quite homogeneous. This is often the rule. It's, of course, possible to store random objects, but it's not very useful. So here we have created a NumPy array containing solely of integers of 64-bit size. You can also generate a NumPy array, such as identity matrix or a list of 1D, a list of numbers increasing from 0 to 15. You can reshape it. You can create random arrays. And of course, it also provides useful tools to do common mathematical operations, such as addition, adding A and B. You can also use the operator plus. A multiplied by B and matrix multiplication is also possible. But this one is not matrix multiplication. This would be a element-wise multiplication. So that's a little bit about NumPy. But sometimes in the real world, we are often faced with heterogeneous data. It's not just numbers. We might be looking at something like a spreadsheet consisting of different columns. So for that, Pandas was built to deal with such kind of data, heterogeneous tabular data. And Pandas became popular over time, and it became the go-to library to read all kinds of such tabular data. So here is one such example from the Pandas repository. And this is a Titanic dataset. So this is a dataset for detailing about the Titanic accident and the number of passengers and what happened to them. So this here we see it's a CSV file consisting of 891 rows and 11 columns. We can look at what kind of data type each column has and what the columns are named. So here, as what is different from NumPy is like you can give names to columns instead of just integer indexes. We can take a quick peek at the top of the CSV file by using this head method. We can also get some useful statistics quickly using describe method. And we can do some analysis, such as here we are just taking a subset of this big CSV file and then grouping by certain columns what the values are, and finding what the median age and passenger class was. So you can see like what kind of passengers survived and what kind of passengers were more likely to not survive, unfortunately. Matplotlib is also another base library, very useful, used to plot such kind of data. It can be numeric. Here we are reusing the same Titanic data set and looking at the survive column and then making a histogram against age. So that's another way of doing analysis with numbers with just these three libraries. So when GPU programming came later, maybe from the beginning of around 2010, and the other three libraries predates them. So they kind of establish how you would write this programming. So all of these libraries that we are going to talk about, which is cuDF, Numba, JAX, CuPy, they take inspiration from Numpy and Pandas. So we start from the most high level of these libraries, which is cuDF. And cuDF is supplied by this Rapids project. And Rapids project, if you go into their website, you see that they have an equivalent GPU library for a well-known CPU one. For example, Pandas, you have cuDF. Instead of scikit-learn, you have QML. Instead of scikit-image, you have QMage, and so on. So here, let's just time an aggregate operation, similarly what I showed you before. And we also do the same with cuDF. And in cuDF, you see that the syntax looks very similar. And it's also possible with cuDF to run pandas code without changing the code. But here we don't see any benefit. And the most likely reason is that the data was either not too big, so it's only a few kilobytes big, and the aggregation operation is not fully parallelizable operation. It's a reduction operation, so it cannot be very efficiently parallelized. So because of that, we see a disappointing result. But instead, if we look at a more larger data set, for example, here we are looking at the New York City taxi data, which the New York government provides. This is a description of all the trips that the New York yellow cabs do. So here I have pre-downloaded it, and you can see the size of the data. It's a few millions of rows long, 3 million row long, and then 19 columns wide. So here I'm doing very simple analysis, calculating based on these two columns, which is the pickup and the drop-off, trying to find out what is the average trip duration. And I'm saving the result of the calculation. It took 44 milliseconds to do that. The same operation using cuDF took only roughly 2 milliseconds. So that's a good speed up. Okay, so now here I did a subtraction operation and followed by a mean. What about a similar aggregation operation as before? So here I'm trying to group certain columns by rate code ID and then aggregating the mean for the passenger count, the trip distance, and so on. So the details are not so important as opposed to how fast it gets. Hopefully it will be faster. And yes, it is. So 109 milliseconds with just pandas and with cuDF data frame. It's only 21 milliseconds. So just to drive it home, here I'm plotting it again. The x-axis is log scale. So whatever improvement in performance is very, orders of magnitude of improvement here especially. So here we see that by making small changes in the syntax, you can get improvements into even data frames by choosing a different library. Let's clear some data. So what if we are not dealing with such kind of tabular data? We are dealing with NumPy-like arrays. So then one very useful tool is Numba. And Numba, what it does, it can transform Python NumPy code into very fast machine code using LLVM. So LLVM is a virtual machine which was used to build C compilers and even Fortran compilers nowadays. But Numba uses this LLVM representation to generate GPU code as well. So Numba has support for CUDA. How it does is, so here we show a very silly example where we construct an array, a 2D array, 100 by 100 size, and then feed it into a function which loops into it and calculates the sign for every element and adds it into a float. We see how fast it goes. And to use a Numba, what we do is we add this decorator called JIT. JIT stands for just in time compiled. And then you can also add this no Python true, which escapes the infamous, Python JIL. So it kind of evaluates everything in using pure LLVM code. So if you do that, it will be much faster because here you don't interact with the Python interpreter. And for such kind of code, it's very useful to use Numba. And Numba is not limited to just the simple JIT decorator. You can also be more expressive with other kinds of functions which operate element-wise. Such functions are called ufuncs or gufuncs. Ufunc stands for universal function. So this is a NumPy terminology. A universal function is something which operates on every element of an array. And a gufunc is a generalized universal function which can operate on every vector of an array, let's say, every small block of an array. So you can write a function which operates on just one element, such as here, we are using the Python standard library math, which operates only on one float, and then apply it on all elements at one stretch by using the vectorized. So NumPy also has a vectorized decorator, and we show here how it compares to the Numba version. So if you're going to not vectorize it, you will be forced to loop over it. But when you vectorize it, you need to specify what the for NumPy, you need to specify what the output type is, which is float here. And for Numba, you need to specify both the output and the input types. And also the target, so which tells you what kind of compiled function you get from Numba. Here it will compile for CPU, and here it will compile for GPU. Let's see how that goes. Oh, by the way, of course, it's always possible to write NumPy functions, but that's not the point here. Here we are trying to show how this vectorized decorator works. NumPy functions are often automatically vectorized. But back to the problem at hand. So here we construct input metrics randomly initialized. So if you're going to use without vectorizing, you need to loop over it, as I mentioned before. And then let's just run all these 4 variants and then time it and see it for comparison. So yeah, here we get it. And I think right now, because I'm sharing the screen, so the NumPy vectorized version does offer only a very small benefit right now, but it should be a bit better than that. But the point is, if you use Numba instead in this, you get significant improvements in performance. So yeah, if you don't have a predefined built-in method from NumPy, then sometimes you need to write your own algorithms, and then this ufunc, gufunc can come in handy. Another thing which is important when it comes to GPU programming is sometimes you need to move the data on your own, and that can add a significant overhead. So if you don't do that, the data can be moved from the device, from the host to the device and back without you realizing it, and that can significantly slow down your execution. But if you want to do that hand holding, Numba also offers that. It offers that through this two-device method, or two-device function. So here we are using that to construct, to send a NumPy array into the GPU device. So let's just do that. And then we also create an empty array in the GPU, which is called C here. And then if we have a function which is defined using Numba CUDA JIT, then if we pass on these CUDA arrays, CUDA device arrays instead, then we can write the code for every thread, every element. So every GPU thread would work on a certain element here in this device array. We may also would like to do some bound checking here. So that's what we do here. And we can get the thread ID from using this Numba CUDA grid function. So we can time this by, we can run this function for all elements using this for all. It's a bit of strange syntax, but this is how it works. So we span this function for all elements of A, and then copy back the result using copy to host. So that's one way to do that. Another way is you can specify the number of threads you want to use and how you want to divide so that you don't over parallelize. Here it's a very small GPU, so it doesn't make a difference. But if I do that, you can see that you can, instead of using this for all, you can use this square bracket syntax, saying the number of blocks and the number of GPU threads you want to use. This is a bit more, low level or medium level hand holding, if you will, to micro optimize it. Very similar to Numba is another library called JAX. JAX also was originally made to construct neural networks, but JAX has a lot of good functionality which can be used for general computing, generic computational loads. So in JAX, quite similar to CuPy, which we'll be discussing in the next section, It has a drop-in alternative for some of the NumPy functions. You can get that by importing jax.numpy. Similar to Numba, we also has a jax.jit decorator, which can JIT compile things. These functions can run in GPUs. It has support for CUDA, and also recently they're adding support for ROCm. But if you don't have a GPU, it can work with CPU as well, just like Numba. But unlike Numba, JAX only works with certain kinds of code. Like it has some restrictions on how you will write the code. You cannot generously add for loops and expect it to work as it is. But here are some examples anyways. So here I'm constructing a 2D NumPy array, which is 10 rows and then 10,000 columns. And then adding a couple of not a number floats. And then what I'm trying to do is trying to compute the non-percentile along the rows. So I'm computing, sorry, along the columns actually. So I'm computing this, and this is very well known to be a very slow operation in NumPy. And it becomes even worse the more columns that you have. But if you use the JAX NumPy alternative, and here you just change the import to jax.numpy, then you get a decent performance benefit of at least 2 orders. So that's how you use jax.numpy library. You can also JIT compile to add more performance on top of that. So here I'm revisiting the same example that we showed for Numba before, and then comparing the NumPy vectorized version, and here is the JAX version with JIT compiling on top of it. And we are feeding, how much is it? It's 10 million long NumPy array, computing a small linear algebra expression vectorized. And then we see that there is JAX version takes only a sixth of the time compared to the NumPy one. Here, JAX automatically takes care of, sending the array to the device. But if you want, you can do that manually. And the way to do that is you can query the kinds of devices that you have by using JAX.devices. So we see that we have a CUDA device in the laptop that we are working with right now. And then you can take the NumPy array that you have initialized and put it into the device using jax.device.device put function. If you do that, then the data resides now in the device. And then it will be even more faster. So if you compare all that together, so you have the NumPy version and JAX giving you a decent speed up. And then if you do the data transfer yourself, it's even better. So that's about JAX in short. Over to CuPy now. CuPy was designed as a drop-in alternative for a lot of NumPy and SciPy operations, bit similar to jax.numpy that we just saw. So the only thing one would have to do is you need to replace NumPy with CuPy, and if you need to replace SciPy, you need to replace it with CuPyX.SciPy. So here are some tutorials for further readings, and we'll try to show how it works here. So here, if this is how you create a NumPy array, the CuPy version looks very similar. And it's the same if you want to compute a norm of the array. You get the same results. So although in the implementation it's different, it's It's the same answer down to the last digit. Let's take a look at the performance now. So here we are trying to evaluate the performance for a 2D array with NumPy first and then with CuPy. So we see a small improvement here with CuPy. I limited this to a very small array size. So the larger the array, the better will be the performance gain. So if you think that CuPy is just a clone of NumPy, you can do more with CuPy as well. So that you do that by creating your own code, your own kernel. Here we try to do that. First we create some input data, which we call it x1 and x2, a 2D matrix written 0 to 24, and then empty output array. And the simplest way to do, you write your own code, which operates on every element, is by using element-wise kernel. This would create a function by generating the code and then compiling it for you. But you need to specify what the data types of the inputs are for each element and the data type for the output. And then finally, the expression. And we can call it whatever you want, but then you can import it using an equal to sign and assign it. So here we do that. And once we pass these to this input variable, we see that we get the sum of it, and then we get the double here. So here we get the output back as a return value. A more complicated way is to use raw kernel, but to make use of that, you will have to know a bit of CuDA coding. So here is an example of how to use this raw kernel approach. Very similar, but it has a little bit of boilerplate. A difference is you also need to pass the resulting output variable. You cannot return it back. PyCUDA is a bit similar to what we just showed for CuPy. In PyCUDA as well, you can create your own kernels. So here, what we are trying to do is we try to create some input data. We transfer it from host to device using memcopy from PyCUDA. PyCUDA is, I would say, is maybe one of the most low-level libraries that you can get if you are using CUDA. And then you have to write something which looks like a CUDA code to get a module or a function defined in the module. So here, this is how you do that. And then you can get back this function, the Python equivalent of this function, by using mod.get function. But to execute this function, you also need to specify the blocks. And you also need to transfer back the result by using memcopy again. So here we do that, and then we get that back. But PyCUDA also offers some easy-to-use APIs like this GPU array module, which will give you a more NumPy-like expression for doing GPU computation. Although the kind of mathematical expressions that you can do with PyCUDA is quite limited. But yeah, you can read a bit more here what is possible with PyCUDA. So yeah, that was a very fast overview of all these popular libraries that you can use to do GPU programming. So yeah, thank you.